Swayam Prabha. Digital India. Educated India.
Let us continue our discussion on review of the course. In fact, in lecture 30, I have given review of the course done till that time. And this review lecture, you can take it as a continuation of that. So, if you look at these two review lectures, you have a complete perspective of what the course is all about. You know, the main focus of this course is to look at what is the typical variation of stress in an axially loaded member, in a beam subjected to pure bending, and a shaft subjected to pure torsion. And you know, we have done this based on inference of photoelastic fringes, at least for axial loading and bending. And when you look at for axial loading, it is uniformly distributed. On the other hand, when I look at it for torsion, this is varying as a triangle. This is the variation of shear stress. And if you move on to the beam, which is transmitting a constant bending moment, here again you have a triangular variation, but this variation is for a normal stress, which is known as bending stress. And you know, whole of this course centers around development of this torsion formula, and then your bending formula. And for an axially loaded member, the elongation equal to PL by AE is a useful relation which we will use it in other contexts of the course also. And you know, we have seen that you have a simple tension test to find out the Young's modulus and yield strength. And you can also use the same tension test to find out the Poisson's ratio. So, you have ASTM standards available for this, and one way is to put a strain gauge transfers to the loading, and you measure the strain transfers to the loading and also along the loading direction, and Poisson's ratio is given as minus of transfer strain divided by the longitudinal strain. And you have ASTM standards D3039, which lists out what precautions you need to take to measure Poisson's ratio. And we have also looked at there is a drastic reduction of the cross section when the material reaches the necking point. So, it is better that you consider the variation in the cross section, and if you plot the true stress as P by AI as the current area of cross section, and also define strain as L naught to L dl by L, L and L by L naught, you have a true strain graph. Instead of drooping down after necking, this will increase as until the ultimate tensile strength. And we have also looked at the stress strain relations, because in a tension test you apply load only in one direction. When I have all the stress components exist, the normal strains are related to normal stress, and shear strain is related to only the respective shear stress. So, that is the speciality of isotropic material. It makes our life extremely simple. When I move on to an anisotropic material, a normal stress can introduce shear, and a shear stress can introduce normal strain and normal stress. So, it is very complicated to handle. So, it is also known as generalized Hooke's law in a simplistic sense, and we have also looked at how many elastic constants that you require to characterize an isotropic material, because we have seen what is Young's modulus E, shear modulus G, and Poisson ratio nu, and we have also developed the bulk modulus. So, we have 4 of them discussed. Out of these 4, how many are required to characterize an isotropic material? So, if you develop the interrelationship, and for interrelationship what we have looked at is we have effectively used the Mohr circle of stress and strain for an isotropic material. If you scale them appropriately, the same principal stress directions or same as principal strain direction. So, you can look at what happens by re-looking the shear stress, pure shear stress as combination of a tension and compression and invoking the stress strain relations. It is possible to establish an interrelationship between Poisson's ratio, Young's modulus and shear modulus. So, you have this from the strain transformation law, and you have the definition of gamma xy based on stress transformation and also this Mohr circle of strain. You can simply write this as epsilon 1 minus epsilon 2, and from your stress strain relation I have gamma xy is tau by g. And when you look at from your understanding of principal stress and strain, I can write out independently epsilon 1 and epsilon 2. When I substitute it back, I get a very interesting relation, g equal to E by 2 into 1 plus nu. On similar lines, we have also looked at how to find out the interrelationship between bulk modulus, Poisson ratio and Young's modulus. For that, we developed the concept of volumetric strain, that is simply addition of all these normal strains. Volumetric strain is nothing but epsilon xx plus epsilon yy plus epsilon zz. Using this, we have revisited what is bulk modulus. It is given as pressure by volumetric strain, and that we got the expression 3 sigma 1 minus 2 nu divided by E equal to sigma by k, and from this you get k as E by 3 into 1 minus 2 nu. So, what you find here is it is enough you have only two elastic constants to characterize an isotropic material. It is the greatest simplification that we have achieved. Okay, and we have also looked at what are the extremum values of Poisson ratio. When nu is 0.5, k becomes infinite, volumetric strain becomes 0, the material becomes incompressible, and when nu is minus 1, you have the other story for g. So, the bounding values for the Poisson ratio is from minus 1 to 0.5, and we have seen cork is a very interesting material, it has a Poisson ratio is 0, whereas rubber has a Poisson ratio of 0.5, and we have also seen negative Poisson ratio comes to advantage when you want to develop a stent for all your arteries and other blood vessels. And the generalized Hooke's law for an if you are considering anisotropic materials, how these are related. Independently, we have 9 stress components and 9 strain components. So, you may think that you may require 81 elastic constants. We have this as sigma ij equal to capital E ij kl. This is known as elasticity tensor, it is a tensor of rank 4. You may think that you will require 81 elastic constants, but if you look at strain tensor is symmetric, this reduces to 54 elastic constants. If you say stress tensor is symmetric, then it reduces to 36 elastic constants. And if you look at strain energy density function, and if you differentiate with respect to epsilon ij, you get sigma ij. This is nothing but another statement of Castigliano's theorem, and the order of differentiation does not matter. So, I have E I j k l is E k l I j. This reduces to 21 elastic constants. So, if you have an anisotropic material, you may require 21 elastic constants to characterize an anisotropic material. Look at, when I have an isotropic material, I need just 2 of them. So, it makes your life extremely simple. That is one of the reasons why we want to have analysis of isotropic material. Even in situations where it is clearly not isotropic, we make that simplification. Then we have also looked at stress strain temperature relations. As long as you do not constrain, you have only thermal strain. The moment I constrain, then what I have is I also have stresses developed. And if I want to write the thermal effects affect only the normal strain, I have an additional term alpha T minus T naught. Okay. So, it is actually alpha delta T. It is not affecting the shear strain in case of isotropic materials. Even though we look at what happens to orthotropic or anisotropic material once in a while, our focus in this course is confined to isotropic materials. And we have also looked at what happens to a hoop subjected to a temperature change, and then we brought in geometric compatibility. We said that tangential strain should be identical in the interface, and we also determined the stresses, and we have also plotted. See, across this, you maintain the compatibility of strain at this interface, but when I plot stress can be discontinuous. And in the case of a hoop, we have simply said it is like you have a circular one, it is opened up, and then you are actually applying a axial tension. So, it is supporting only a constant stress that you know as PR by T. So, when you plot the stress variation, the variation would be like this. And we have also looked at if you have to strengthen a beam made of a soft material, you can put a steel on top of it, top of aluminum, top as well as the bottom, so that you maintain the symmetry. And when we plot the strain variation, the strain variation is linear. However, when I plot the stress variation will have a step at the interface. And the other subtle point is, because I am looking at bending, even though the thickness are small, there would be a linear variation, because you have the factor y coming in the strain expression as well as stress expression. It is not going to be constant. In the case of a hoop, it is constant. In the case of a bending, it varies linearly even though thickness is small. It is a subtle point for you to note. And we have also looked at basics of photoelasticity. Since now you have the knowledge of stress, strain and also principal stresses, what would be the nature of contours of sigma 1 minus sigma 2? We have sigma 1 as sigma x and sigma 2 equal to 0 in one section of the beam. Since sigma x varies linearly, sigma 1 minus sigma 2 contour values always remains positive, and if you plot them analytically, you get essentially parallel lines, which is also verified by your photoelastic experiment. So, this is another indirect validation of photoelasticity giving contours of sigma 1 minus sigma 2. So, you have beautiful color variation, and we have also seen use of photoelasticity in several other applications, and your stress tensor is shown. And we have also looked at how to measure strain. There are multiple methods. The moment you go for measurement, the resolution and range of each of the technique you have to look at. Depending on the capacity of the technique, it has a resolution possible, like you have a distance measurement by a scale or a vernier caliper. So, you should choose an appropriate technique that would meet your requirement. If you are working on this range, I can go only for Maury interferometry. If I work in this range, which is like in a Gudgian pen, I can go for a grid method. And you can also apply photoelastic coating to reveal the strain patterns, and you have the Moire, which also gives you displacements. And you have a brittle coating where normally you do not want cracks. Here crack is the information. Crack provides the material fails in a brittle fashion. So, you get contours that are when you draw the tangent to that, you get the principal stress direction, fine. And a general purpose analysis is possible with a strain gauge, but for special application you need to go for appropriate experimental technique for strain measurement. And one of the discussion in the case of strain gauge is, how do I connect the strain gauge and a Wheatstone bridge? If I do not connect them properly, I may get wrong results. In transducer applications, you want to maximize the signal. So, you know how a cantilever beam behaves because you know bending now. When I apply this load, this is subjected to tension and this is subjected to compression. So, these are strain in opposite direction, connect them in adjacent arms so that strain magnitudes get add up. Okay. So, you amplify the signal in a transducer application. I can also do the amplification by putting two strain gauges on this, but if I do not connect them properly, suppose I connect them like this, what is the result you will get? You will get twice the signal or zero signal. I will get only zero signal. So, you will also have to handle the Wheatstone bridge appropriately. And we have also looked at how to extend this for torsion, because strain gauge by itself can measure only axial strain, fine. And we have understood what way shear stress can be looked at as combination of tension and compression, and using that and looking at the Mohr circle, you can have the justification. Using this, we have identified that strain gauges have to be aligned at 45 degrees to the axis and connect them appropriately in the Wheatstone bridge, so that I can quadruple the signal. That is the advantage. So, I can measure torque with much more accuracy when I use that as a torque meter. Okay. You have torque wrenches which measure the torque. So, you have definite applications. How do I put them? This is very important, tied to how I have pasted it on the shaft. Then we moved on to torsion. We have looked at circular cross section. To understand circular cross section in a simplistic manner, we have also looked at a square shaft. In a square shaft, you have a warping which is absent in a circular shaft. That made your life lot more simpler. That is the reason why in this course, we choose the cross section and the loading so that plane sections remain plane before and after loading. We postpone torsion of circular cross and non-circular cross section to the next level course. It is not that it is not solved, it is solvable, and Saint Venant is the first person to solve it. Okay. So, plane sections remain plane before and after loading. We have done it by a thought experiment. Okay. And then you can also see it visibly when you take a simple circular shaft, draw the lines and then twist it. Okay. And we have also a nice animation. You look at the animation, you understand what all we have done for finding out the strain components. And this shows the experimental information, and this shows the drawing in a systematic manner. So, you find out what is the strain that is existing. You have that as the reference axis is given as r theta z. So, I have only gamma theta z existing, that is given as r d phi by dz, and gamma r theta is 0 and gamma r z is 0. I have only gamma theta z which is r d phi by dz. So, we have used this to develop the stresses, okay, and strain, stress and equilibrium equations, and in the process we have also looked at a quantity like this, which when I substitute I get this as r squared dA, that is your polar moment of inertia, and we develop it for a circular shaft. We also extend the same ideas to a hollow shaft. The same ideas are equally applicable for an hollow shaft, and there is also interchangeably use IZ or IP, because I said that in bending of beams IZ has a different connotation. So, it is better to look at as IP for circular shaft when you are doing torsion, and look at IZ for when you go for the bending of beams, or you can simply say that as I, if you understand how the equations are developed with respect to the coordinate system. And this is the celebrated equation that you have. This is developed for a circular shaft transmitting constant torque. And what we do is, when you have a twisting moment, pick out that twisting moment at that cross section, find out the torsional stress. Okay. Then we moved on to bending of beams, where we have looked at a very soft beam, and we could understand that straight lines get rotated, and we have understood the plane cross sections of the beam remain plane during bending. That is what you see here, there is no warping. And you have cross section which is perpendicular to the undeformed axis of the beam remains perpendicular to the deformed beam during bending. That is very important. Okay. This implies that originally parallel lines the beam gets rotated. It is very clearly seen in this experimental demonstration. And when we go into the results, we have the stress and strain in pure bending. It is very important that theory is developed for pure bending, a beam transmitting only bending moment, nothing else. So, we have the expression for epsilon x, we have the expression for the sigma x, and we have the stress tensor, and this final result is credited to Coulomb. So, you have to recognize that the stress varies linearly over the depth of the beam, and the central core is not contributing to load share, which is used by nature in developing your bones. Your hemoglobin gets developed in the soft aspects of the bone, and we have the relation E by rho equal to mb by Izz, which finally when you look at all the other expressions, you have the famous flexure formula mb by Izz equal to minus sigma x by y equal to E by rho, because later on we also dropped this Zz just to speed up your writing. Once you understand the context, what is the axis and what is the kind of moment of inertia talking in this context, it is convenient to simply write and indicate moment of inertia as I. And you have the torsion formula, you compare, they are very similar. Fine, it is easy to recollect how these are written. And the other question we raised, can beam theory be extended to a cantilever beam? What is the difference? In the case of a cantilever beam, in addition to bending moment, it also transmits a simple constant shear. Even a simple constant shear modifies the bending moment along the length of the beam. So, the recipe here is you have the flexure formula, okay, and simply pick out what is the bending moment at this cross section, then you say what is the bending stress using the flexure formula, that is permitted. And we have also seen, even though the cantilever beam warps, there is no coupling between shear and bending as long as you are having a slender member and the depth of the beam is very small compared to the length. If the depth is comparable to the length, then you can have coupling effects. That is considered as a Timoshenko beam, and you have different theory developed. Remember, such problems are solved. It is not done in this course. And we have also looked at other discussion, how do you have sigma 1, sigma 2, and then whether you have neutral axis, and in isotropic material, what is the advantage, all these related discussion we have done. Whenever we have a beam transmitting a variable load or even your uniform weight, there are multiple ways books bring out the expressions. If I have the W acting upwards taken as positive, I will have the expression dV by dx equal to minus Wx and dm by dx equal to minus V. On the other hand, if I develop the equation with W as acting downwards, the only change is dV by dx goes to Wx, it becomes positive. So, you will also have to understand a subtle difference. If you do the mathematics systematically, there is no problem, but if you want to interpret it based on sign convention, you have to see which way you have developed the equations. And one of the subtle points in the case of bending is how shear gets developed. To understand this, we have taken a layered beam and we find they are slipped, okay, as the loading is applied. You could very clearly see slipping of layers, and you can also imagine something is holding it, that is why the layer is not slipping in a beam which is rotated like this. Okay. Here the rotation is very small and this edge remains straight, whereas the same height of the beam with 4 layers, you have this jagged edge that clearly shows there is something is holding the surface. Okay. So, on that basis we developed the mathematical expression for the shear stress, and this also shows how much is the angle or the slope when the beam is one unit but with the different layers, which brings out very clearly the role of shear in the beam analysis. Okay. And even though we have said shear is important, there are other concepts also we have learned. A bending stress, if you plot it with some scale, is triangular and you have compressive and tensile. And in order to illustrate that shear stress varies parabolically, many books show this big, but they do not give an insight what is the relative magnitude. That is also very important. Even if you consider a simple problem of a rectangular cross section subjected to 3-point bending like this, for this problem, if you calculate the shear stress in actual magnitude, if you plot, it is as small as this compared to the normal stress created by bending. That is the reason, even though shear is important in certain instances, we are neglecting it because its actual magnitudes are considerably very small in many applications. And we have also looked at how to put the stress tensor. You have the comparison in terms of numbers, in terms of tau xy max divided by sigma x max. I get this as 1 by half of h by L. So, if I have h by L as if I take this as 1 by 10, so it is 20 times less, okay, compared to the normal stress. So, that is the idea that you should have. And we have also looked at how to write the stress tensor at specific location of the cross section. This is the cross section that we are talking about. You can also write the stress tensor. This is compressive, so I have put this as minus sigma xx 0 0 0. And when I have this as the tension side for this problem, I have sigma xx 0 0 0. And when I look at the center, because this beam is also transmitting a shear force, so what I have here is I have 0 tau xy 0. When bending is maximum, shear is 0. When shear is maximum, bending stress is 0. That is the interesting aspect of what happens in a beam. Suppose I take a point in between, this will have sigma xx, tau xy and tau by x. That is dictated by the problem. Okay. And we have also looked at how to write sigma 1 and sigma 2. We always say that one should be algebraically the largest. When I have this as compressive, this becomes sigma 2. Very subtle point, but it is also very important. That is a convention that we have used. We will always have sigma 1, sigma 2, sigma 3 arranged algebraically larger. Okay. And we have also looked at the inconsistencies in shear stress formula. You have an issue when I have it in the junction. Okay. Nevertheless, we use these expressions because we get the numbers reasonably for us to play with. And from your free surface concept, I should have my this flange, this should have 0 stress, but your shear stress formula does not give it. And in the transition region, what you have here is this, you take the length of the flange and you get a smaller magnitude. The moment you come to the web, suddenly the stress magnitude increases. That is correct, that there is no problem. The problem comes in other zone, okay, and you have this tau xz varies linearly because you take q like this, okay. And the other important limitation is when I look at here, this is the free surface, I should have 0 shear stress, but you have shear stress here, and that you will have to take it with a pinch of salt. These are fuzzy zones. Shear has to be 0, but shear formula predicts a small value. But we have already looked at, from a mathematical point of view, you may have some number, but if you compare the magnitudes are very small. And this is a reasonably simplistic analysis of an open cross section that we could do in the case of beams. From what we have developed for the cross section which has one plane of symmetry, we could exploit that flexure formula for a wide variety of problems than what we have learnt it for torsion. Okay. And there is also a very interesting concept once you look at open sections. When you observe this, you find that this is bending as well as twisting, and when you apply it along the shear center, it only bends. Okay. And this is another angle cross section, and if you look at this, this also bends and twists. The shear center is actually this corner. I was unable to put my pen there, so it was slipping. I just put it next to this. You can very clearly say that this is only bending, there is no twist, but while bending, it has bending in two planes. One plane is like this, another plane is like this. It is bending like this, it is also bending like this, and that we said it is an unsymmetrical bending. Is the idea clear? When it is bending in two perpendicular axes, you have this as unsymmetrical bending. And we have also looked at another typical cross section used in beams. You have T beams used in many applications. This is very interesting from the point of view of writing a stress tensor, because if you write stress tensor at A, it is very simple. Simply sigma xx is existing, and you also have the expression from your flexure formula. And for the point B, which is on the centroidal axis, which is also the neutral surface, this is made of one material. Okay. So, I have this as only tau xy and tau by x, and when we also have the expression tau xy as vq by b izz, and your typical bending stress variation is like this, and your shear stress variation tau xy is like this. And when you make this as modulated for the actual values, these values are very small compared to the bending stress. And when you go to the point C, I have put this as minus sigma xx. And interesting aspect is what happens at a point D, that is what is put here. I have sigma xx, tau xy as well as tau xz. You should recognize that the stress tensor is more populated. Okay. So, we have learned how to get the expression for stress magnitudes, whether it is axial stress, shear stress in torsion, or bending stress in bending, or shear stress in bending. When you get that as those quantities, that appears like scalar, but you should also put it in the matrix form so that you recognize that this is a tensor of rank 2. Not only this, when I have combined loading, if you write it as a matrix form, you can add them if you take the axis appropriately, which we have also solved a problem of a femur subjected to tension, torsion and bending. Combined loading is the order of the day. Any simple problem has only combined loading. We learn them separately. And one of the concepts that I have said that you lack is how to move a force from one point P1 to P2. If you master this, when I move this from P1 to P2, I need to have a force as well as a couple. You can comfortably write the bending moment diagram and shear force diagram. You take more time because you have not mastered this. I am repeating it again and again. And even when you look at a simple tension spring, if you find what is the load which is acting, when I asked you to find out the forces, you are struggling to get it. But if you look at how to apply this concept, which I am doing it again, when I move it along the axis, nothing happens. I can move the force freely along the axis, that is principle of transmissibility. But if I move from this axis to this, I have to look at, I will have a force as well as an appropriate couple. Okay. Here you are getting this couple in such a manner that this is along the axis, so it is a twisting moment. So, I will have a twisting moment as well as a shear force. Then we moved on to how to analyze the torsional spring. You say torsional spring, but what is the major force it is transmitting? Its major force transmitting is bending. That is again, I have a force here, I move this force, So, this gives me a force as well as a couple. This couple is a bending moment, and when I move from this to this, I have a force as well as a couple. This is a twisting moment. So, you have to use this aspect of moving a force from one point to another point. It is not trivial, which is not emphasized in the books. I have emphasized it repeatedly so that you get the idea of this concept better, and you can solve seemingly very complex problems in a jiffy. Now you have the background to analyze these problems. So, do not simply say that when I have a sketch like this, a simple spring gets stretched, it is transmitting axial load. Do not say that. It is actually transmitting a twisting moment. So, this transmits torsion and this transmits primarily bending. So, you have to know the difference. And I said that even though I say shear magnitudes are small, it matters when I go very close to the load application point. If at all I apply strength of material solution, I must apply it away from the point of loading. Okay, I must do it only in a zone away from the point of loading. But if I go close to the load application point, this is done from theory of elasticity solution. This is what you have in an experiment. This matches very well with theory of elasticity solution, and look at what happens in the case of strength of materials. It totally misses out this aspect because we have never considered, we have taken shelter under Stein-Winant's principle. So, you have to consider that near the load application points, the shear magnitudes are very high. Just below the surface it reaches a peak. At the surface it is still 0 because it has to satisfy that free surface requirement. And these stress magnitudes are comparable to the bending stress. So, failure can definitely happen unless you reinforce these areas, and this is done in practice. People have stirrups to support this. And we have also looked at another deviation. Suppose I have a uniformly distributed load, which is a common load in all civil engineering construction. You have the self light, and if you look at the strength of material solution, even for a rectangular cross section, which is very well done in strength of materials, is not in order. There is a small variation in your normal stress. It is not linear, but it is having a small nonlinear component. And in addition, we have said in pure bending there is no normal sigma y stress component. That is correct. But when I have a situation like this where I have distributed load, I do have normal stress, and theory of elasticity accounts for this. And here again I want to caution you that this is not drawn to scale. None of these quantities are drawn to scale. The focus is only to show the variation, shape of variation. To accentuate the appreciation of shape of variation, it is drawn big. If you draw it in real scale, they will appear very small. All these three quantities will appear very, very small. And we have also learned how to analyze a reinforced concrete beam using the same flexure formula. We imagine that the concrete beam is like a section like this and a hollow section connected by a thin web. Okay, and that's how we have analyzed it. It's all engineering analysis because only the rods, steel rods take the tension load. Concrete is very weak in tension. And we have also looked at various methods to determine the reflection of beams. So, we have double integration EIZZ d squared v by dx squared equal to mb. And if you use the interrelationship dm by dx equal to minus v, dv by dx equal to minus w, then I get quadruple integration, that is load deflection EI d power 4 v by dx power 4 equal to w. We have been able to take out EI out because we are discussing a beam of constant material and constant cross section. Otherwise, EI would be inside, d squared by dx squared will be there. That way also you can analyze. And when you do this double integration or quadruple integration, you get the variation of slope and deflection along the length of the beam conveniently, no problem. And we have also looked at that this is useful even for statically indeterminate problems. Then we also looked at moment area method, method of superposition and energy method. These are applicable for at specific locations. If you want to find out the deflection slope, you are in a position to do it quickly. Okay. And moment area method, people also say, even if I have EI changes, I have to scale up my bending moment diagram in that region with the appropriate EI. So, beams of variable cross section, or if you change the material, moment area method is also a good choice for you to find out the deflection at specific locations. And one of the aspects in bending is deflection is you have to find out what way the boundary condition to be written for a simply supported end. It will have a slope, it will have deflection as 0. On the other hand, if I go and do that as a fixed end, you find immediately the slope goes to 0. Your deflection is 0, but slope is also 0. And you will also look at what happens in a free end. So, if I have problems of this nature, you should know how to write the boundary conditions. It is needed even for your appreciation of how the deflection can be, because one of the training in this course is to learn how to use method of superposition. There the training is how to draw the deflected shape. Okay. So, you should practice this and then visualize how the beam can have a deflection. That is a very important idea. It helps you to even verify your mathematical development. Okay. And we have also looked at in the moment area method, you get only the, if you calculate the area, you get only the difference in angle of the slopes. You do not get the absolute slope. Okay. Similarly, you get only tangential deviation when I take the moment. If I take TBA, I have to multiply by x bar b. If I have TAB, I should multiply by x bar a. I get only tangential deviation. You should know how to use this effectively to get the actual deflection, okay, or actual slope. And in the method of superposition, as I said, because we are living in a linear elastic regime, I can superimpose independently and add all of them, analyze the problem independently so that the problem is easy to handle, and add them together in a systematic fashion. So, you should know how to draw this deflected shape. You should visualize that. That is one of the important training that you learn in this course. And we have also learned fictitious load method. This is due to Castigliano. He is a very young scientist. He passed away very early in his life, and this theorem was available in his PhD dissertation. It has become very popular, and many developments using energy methods later on owe allegiance to his contributions. So, even if I do not have a particular point and load is acting, if I want to know what is the deflection in a direction or in any other point, I can add a load, introduce a load Q, determine the energy, and then differentiate with respect to, find out the energy, differentiate with respect to Q, substitute Q equal to 0 at that stage, then what you get is a deflection along that direction for that point of interest. So, very useful method. And I also said an extension of this is the development of the finite element method, and experiment is truth. Okay. But when I have the finite element method, I can get the displacement contours, I can get the strain contours, I can get the stress contours, all of that I can do. Okay. And finally, if I plot the stress contours in terms of sigma 1 minus sigma 2, you see this is from an experiment, this is from a finite element analysis. The match is very impressive. You can clearly say that my numerical analysis has brought out the results correctly. What is the difficulty here? You have a boundary of the spanner which is very arbitrary. Even though theory of elasticity we have used as a basis to verify our strength of material solution, theory of elasticity demanded how to write the boundary condition in an arbitrary geometry. That was very difficult. It can handle simple geometries like circles, ellipses and so on. So, one of the greatest advantage of finite element is I can discretize it using an element and handle any arbitrary geometry comfortably, but the solution is approximate. It is not an exact solution, but you go asymptotically to the actual solution, and you have many packages available, and you can learn some of them as part of your future courses. And ultimately, why we have developed all this concept of stress, strain and principal stresses? We wanted to investigate whether the component that I make, whether it will withstand the loads or not, whether it will be strong enough. So, you have failure theories and you have Trusca yield criteria. I said if I have sigma 1, sigma 2, sigma 3 arranged in this fashion, you will never make a mistake if I have sigma 1 minus sigma 3 is taken and compared with sigma by S. I caution, in the case of your simple pressure vessel, both the principal stresses are positive. There is every room that you can apply Trusca yield criteria wrongly to that. You may simply use sigma 1 and sigma 2. You should not forget sigma 3 is 0. And you should also appreciate failure theory is a substitute for good test data. I said for complex structures, people develop very expensive loading rigs, and only then the design is released for human use, because human lives are very precious. And failure theories are based on simple tension tests. How did they approve the theories? By conducting complicated experiments and verifying that the experimental results for unknown load situations which have not accommodated in simple tension test also falls within that yield locus or very close to the yield locus. Okay. And for brittle materials, because for ductile materials you have Trusca, you have von Mises, which are shown here. One is an elongated hexagon, another is an ellipse, and this appears like a circle and a hexagon in the 3-dimensional sigma 1, sigma 2, sigma 3 space. And I also said that von Mises yield criteria is same as distortional energy theory as well as limiting value of the octahedral shear stress. Okay. So, people have verified it from multiple viewpoints, and for brittle materials, because they have a very different values of tensile yield strength and compressive yield strength, they are very strong in compression, and you have a failure locus which is modified by several people. Initially you had one developed by long time back Coulomb, but modified by Moore. Then finally it was modified by Griffith, that is also shown here. And so you have to use principal stresses very effectively to verify whether a material, whether it is brittle or ductile. You have failure theories, and you also have in design what is known as factor of safety. I said factor of safety is a very important design parameter. Even a simple ATA checky can throw you surprises. So, when I have this, I have the stress tensor in this form, and you can write in the design courses, they simply express it in terms of the bending moment and twisting moment. And because the shaft is rotating, you have to recognize the bending introduces stress nature that varies cyclically, because this shows you have the fiber, how the fiber when due to rotation experiences load, which is a very subtle point. Okay. You may miss it. And what is the consequence of this? The bending stress on the shaft introduces fatigue loading as the shaft rotates. In view of this, it reduces further the allowable stress. And all your design courses basically use what is the principal stresses from this stress tensor and expresses this in terms of your bending moment and twisting moment. So, when I have a shaft transmitting torsion and bending, you have a simple expression. They will do and estimate the diameter of the shaft just by using this. There is no torsional stress or bending stress in the expression, they are hidden. Okay. And you do not have to memorize this in your later course, you can derive, and people use this in their design books like this. Okay. Then we said that when you don't have a warning, any failure is difficult to handle. So, one of the functional failure laws is you have a column that suddenly buckles. Okay, there is no material separation, but suddenly buckles, and we have seen that this is developed by Euler in 1757, and buckling is one aspect where we have to analyze on deformed coordinate system. Second aspect is the critical load at which buckling takes is very sensitive to the boundary conditions, and we have looked at how when the boundary condition changes, how the shape changes, and we also said that these are all neutral equilibrium positions. Okay, and the experiment gives you truth, and this is one of the experiments which is very, very expensive, and people also found application for the buckling. Engineers are very clever, they don't leave any physical phenomena go unutilized, and you view the critical load from a different perspective. You take the hinged column as a basis, and you have the critical load as pi squared E A by L squared E, and you visualize other boundary conditions with an equivalent column length. If I have a column of fixed pin, I view this as equivalent length of 0.7 L. If I have a column which is clamped, I view this as a column of length 0.5 L, and if I have a cantilever, I view this as a column of 2 L. Longer the column, more it is prone to buckling. Okay. And last but not the least, we have one of the best explanation for Saint-Venant principle in this course, because you have been trained to look at photoelastic fringe patterns. So, in these three cases, I have a statically equivalent system applied, and what you find is the disturbances die down after a distance, and this distance becomes smaller when this distribution is close to the assumed distribution of uniformly distributed is the one which we require. We say that axial load resistance is developed like this, and this happens at different distances. See, what is the distance that you have to take? One thumb rule is it is equivalent to the longest cross sectional dimension. It is only an empirical approach. Okay. There have been many discussions. There are also certain specific instances where Saint-Venant principle does not work. That also you should know. But for a large variety of problems, Saint-Venant principle is a very useful principle, and you are able to relate it easily by looking at the fringe pattern, because in a axial load I should have a constant color, and how the constant color is obtained you have to look at. And this is by Saint-Venant. Unlike Castigliano, he had the longest life, about 90 years, very active till the last minute. Very, very few people in life are gifted to pursue their passion till the last minute. Okay. So, with these observations, your overview on strength of materials is brought out. So, if you look at these two lectures one after the another, in a nutshell, you know what are the important concepts that we have looked at in this course. Thank you very much.